All right, so now that we have talked about sort of the individual structure of an element, we're going to talk about how those elements can come together to combine to form what is known as a compound. Two or more elements may combine to form what is known as a compound. A compound's characteristics are usually different than those of the individual element, and atoms in a compound are going to be held together by chemical bonds. So what do we mean by a compound's characteristics are usually those different from those of the individual elements? Well, for example, let me get my laser pointer here. For example, the element sodium is a solid metal. Elemental sodium, this is what it looks like. It looks like a solid, shiny metal. Now, here's the problem with elemental sodium. It is highly explosive when it is exposed to water. Very, very deadly, very dangerous. Extra credit points to anybody who wants to send me a YouTube video of somebody being a little bit crazy and throwing elemental sodium into a large body of water. It's really fun to watch what happens. So that's elemental sodium. Elemental chlorine is actually a yellow gas, and it is very deadly, or it's highly toxic and very, very deadly. So chlorine gas, super deadly. Elemental sodium, super explosive. Both of those together seem super dangerous. However, when you combine sodium and chlorine, what do you get? That's right, you get sodium chloride, aka table salt. Sodium chloride, or table salt, is not only non-toxic, it is also non-reactive in water. It doesn't explode explosively with water. It's not a gas that's extremely noxious. Table salt is not only not deadly, but it's actually essential. It's a very important mineral, very important part of our diet, and a very important part of our bodily functions, as we're going to find out when we see how sodium and chloride ions react inside of the body. So this is something I just want to point out. When you see all sorts of fear-mongering about mercury being found in vaccines or certain chemicals, preservatives being found in vaccines, keep in mind that yes, elemental mercury is very dangerous. You should not consume elemental mercury. However, elemental mercury is not what is found inside of vaccines. It's not pure elemental mercury. It's mercury compounds, which are not only inactive, but they are safe. They are not necessarily toxic or deadly or dangerous. So please keep that in mind. You see a lot of fear mongering about certain chemicals that may be found in certain other chemicals, and just keep in mind that pure elements are very different than compounds. Compounds have completely different properties. It's almost, you can kind of think of it just like having a different number of protons changes the element itself. Once you add a proton, carbon is no longer carbon. Once you make a compound, that element is no longer anything like its elemental form. It's not going to behave like its original element. It's not going to react like its original element. Once it's in a compound, it's sort of like we create a whole new creature. So just keep that in mind as you're going forward. But we're going to talk about that ability for these molecules to form, the ability of these atoms to form compounds through chemical bonding. And in order to study chemical bonding, we first have to look at valence electrons. If you remember when we looked at the structure of the structure of an atom, we looked at all the subatomic particles that are found inside the nucleus. What are those? So go back to your notes. Which subatomic particles are found inside the nucleus, and which subatomic particles are going to be found orbiting around the nucleus? What you'll find is that electrons orbit around the nucleus. And what we have are multiple energy shells. Some electrons will orbit very, very close to the nucleus. Some will orbit further away from the nucleus. The ones that are going to be orbiting farthest away or in the outermost shell are going to be called valence electrons. These are electrons found in the valence shell, or the outermost energy shell of the atom. The valence shell is going to be what determines the chemical reactivity of an atom. So the valence shell, and I know we talked about the chemical characteristics coming from the number of protons, but the number of protons determines the number of electrons. The number of electrons determines the number of electrons that are found in the valence shell, which is going to determine the chemical reactivity of an atom. There are a couple of rules that we should know when we're discussing valence electrons. For example, any atom with only one energy shell is going to be most stable with 2 valence electrons. If you ever see that in any of my notes, or really anywhere, E with a negative sign like this right here, that's shorthand for an electron. So any atom with one energy shell is going to be most stable with 2 valence electrons. Any atom with multiple energy shells is going to be most stable with 8 valence electrons. This is what's known as the octet rule, those 8 valence electrons. So we're going to take a little bit of time to look at these locations of electrons found on an atom. So it's not possible to determine the precise location of an individual electron at any given moment. So we have to have a model to approximate where these electrons are going to be distributed. What we're looking at right here, this sort of ball and stick model, this is what's known as a Bohr model. It's one of the more common models. It was developed by the physicist Niels Bohr. In a Bohr model, the electron shells are bound to the nucleus, are used to represent the average energy levels of an electron. The negatively charged electrons are going to be attracted to the positively charged nucleus. Inside of this nucleus here, we're looking at an atom of oxygen. If we go to our periodic table, we'll see that oxygen has an atomic mass of 16 and it has an atomic number of 8. This means that it has 8 protons and 8 neutrons found inside the nucleus. Now, does anybody remember what the charges are for protons and neutrons? Once you determine what the charges are for the protons and the charges for the neutrons, write down or tell me what is the total charge of the nucleus. What we're going to find is that we have a overall positively charged nucleus, and the electrons, which have a negative charge, are going to be attracted to that positively charged nucleus. The negatively charged, they're going to be attracted to that positively charged nucleus, and it's going to take energy to push them away and keep them away in their own shells because they're all attracted to this positive nucleus. So we're actually going to have to use energy to push them away and keep them in these outer orbitals. That is what we're referencing when we talk about energy shells or valence electrons. We're talking about the amount of energy. We're talking about the energy it takes to push those electrons away from that positively charged nucleus. The more distant the shell is, the more energy it takes, and thus we describe electrons being at particularly energy levels in relation to the nucleus. So electrons that are going to be found out here are going to be at a higher energy level than the electrons found down here, because it takes more energy to keep them further away. Electrons have energy due to their relative position, and they're actually able to move from one energy shell to the next. We're going to talk about this quite a bit when we talk about the process of photosynthesis. When atoms absorb energy from the sun, the electrons are going to be boosted to a higher energy shell, and we'll actually see electrons get excited from one energy shell. They're going to bounce up to another energy shell because we add so much energy to them. They're going to store that chemical energy or that solar energy from the sunshine as potential energy by moving from a low energy shell to a higher energy shell. And as they return to their original energy level, they release that energy and transfer it into a form of chemical energy known as glucose. But all of this is something that we're going to come back to later. What you need to know for now is that this position that we see here is a relation to the energy it takes to hold that electron in its orbit. So because the stability and reactivity of the atom depends on the number of electrons in the outermost shell, we give it that special name, that valence shell, or that valence electrons that are going to be found on this outermost shell. So we're going to take this a little bit slower. We're going to back up just a little bit, and we're going to look at 2 different electrons, or 2 different atoms. So what we have here are 2 atoms. Helium has only one energy shell. It has only one energy shell and 2 electrons. How many valence electrons do we have in this helium atom? And is this helium atom satisfied? Is he stable? Remember, you're going to have to go back a couple of slides when we talked about valence electrons. Determine how many electrons do we need in our outermost shell to be stable and happy. And then come and tell me if this helium atom here is happy. Is he stable? So what about this oxygen atom? How many energy shells does he have? And how many electrons total does he have? So once you determine the number of energy shells, then determine the number of electrons he has total across those energy shells. Then I want you to tell me how many valence electrons does he have. So look for the valence shell and then tell me how many electrons are going to be found in that valence shell. The last thing I want to know is this atom going to be stable? Remember, if we have more than one energy shell, we need 8 electrons to be stable and happy. How many electrons does oxygen have in its outermost valence shell? And is he satisfied by having 8 valence electrons? Now here's something that's a little bit interesting that we can do. When we're looking at the reactivity of an atom, we can take the time to draw out the atom itself. We can, if we wanted to draw an atom of nitrogen, we could go to the periodic table. We could see that nitrogen has an atomic mass of 14 and has an atomic number of 7. This means that we're going to have 14 subatomic particles found inside of the nucleus. 7 of those are going to be protons. If we have 7 protons inside the nucleus, we must have a positive charge of 7 inside the nucleus. We have 7 protons, 7 positive charges, an overall positive charge of 7. If we assume that that element is going to be electrically neutral, our total charge on the atom has to be even. Has to be 0. So if we have 7 positive charges inside the nucleus, how many negative charges do we have to have orbiting the nucleus? Or how many electrons do we have to have orbiting the nucleus to balance it out? So if we have 7 positive charges, we have to have 7 negative charges. We know that we can put 2 electrons into the first energy shell, and then after that we can put up to 8 electrons in each shell. So we'll find that if we were to draw a molecule of nitrogen, we would have 7 electrons total. We would be able to put 2 electrons in the first energy shell. We would have 5 electrons in the outermost shell. Is that molecule going to be happy and satisfied? Has he followed his octet rule? The answer is no, he has not. He wants to have 8 electrons in his valence shell, but he only has 5. So he's going to have to do something. He's going to have to bond to someone or something in order to be satisfied with his 8. So each atom in a group has the same number of electrons in its valence shell. One thing I want to point out is that you can add up or you can break down into shells the number of if we know that we have 7 electrons in nitrogen, we can draw a model of nitrogen in order to determine how many valence electrons it has. Or we can take a look at the group number. What you'll find if you look at the portion of the periodic table is that we have what are known as periods going across. So period 1 includes hydrogen and helium. Period 2 includes lithium, beryllium, boron, carbon, nitrogen, oxygen, phosphorus, and neon. Period 3 contains sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chloride, and argon, so on and so forth down the periodic table. We also have groups going vertically. And what you'll find is that these atoms are arranged such that the group number indicates how many valence electrons it has. Nitrogen is found in group 5 and has 5 valence electrons. Carbon is found in group 4 and has 4 valence electrons. Oxygen is found in group 6 and has 6 valence electrons. If you would like to, I would love to draw and discuss certain examples of this. So for practice, why don't you take fluorine right here and you draw a model of fluorine. Look at its atomic mass and its atomic number to determine how many protons and neutrons are going to be found inside of that nucleus. And then draw the valence energy shells around it, starting off with its first energy shell, which will only have 2 electrons in it, and then building out from there. Use that to determine how many electrons are going to be found in its valence shell.